Now it is section 4.6, applied optimization. Optimization is to find maximum or minimum. In this section, you will solve some applied optimization problems using derivative techniques. In each problem, you will have two components. One is given, the other one is the unknown quantity to be optimized. For example, for rectangular regions, the perimeter is given, then you may try to optimize the area of the rectangle. For these problems, the most important thing is you have to understand the problem. What is given, what is the unknown quantity to be optimized? You have to recognize these two things, first of all, and then by using some relation, you have to express the quantity to be optimized as a function of a single variable. And you can use now derivative technique to get the critical point and to figure out which one is maximum, which one is minimum, and so on. Let's try to solve these problems, and you can understand here the sentences in the strategy. Okay. Example 4.42. What is the smallest perimeter possible for rectangle whose area is 16? Okay. And at the moment, we want to find the dimensions. Okay. Now, for this problem, we have to minimize the perimeter. And the given is area is 16. So once you visualize the problem like that, and it's a rectangle, so we may say the length of this side is x, length of this side is y. Then now area is same as xy, which is given to be 16 square inches. Now what is perimeter? The perimeter is same as 2x plus y. Right? We have to minimize this quantity. Okay. And here, but we have to express the quantity as a function of a single variable. So for each problem, I'll say again, most important thing is understanding the problem. And especially in mathematics, for study problems, there are three components. One is given, and the second one is the unknown, and third one is condition, how they are related. And that is now three components. If you understand these three, then you really understood it. And for this optimization problem, now you have to express the quantity to be optimized as a function of a single variable. But right now, perimeter is a function of two variables. Now by using this one, you can change it. And from this one, now y can be written there's a 16 over x. So here, the perimeter is same as 2x plus 2y, and so that now there's a 2x plus 2 times y is 16 over x. Okay, let's rewrite it. So there's a 2x plus now 32 over x. Now this is here the equation in single function of a single variable. So now you can use derivative technique, and we consider it as a function of x, so that p prime, that is this derivative with respect to x, then that will be 2, and now minus 32 over x squared. And here 1 of x, the derivative is minus 1 of x squared. So if you put this as 0, then if you solve this equation, then that is critical point, right? Okay, from this one, now x squared must be 16. Okay, which means that x is now plus minus 4. However, x cannot be negative. And we didn't say in the beginning domain of x. However, x is representing a length. So length cannot be negative, which means now here x must be 4. Then when x is 4, now from this equation and also from that equation, you can say that here y must be 4. And we found the dimensions, x is 4, y equal 4. At the moment here, now the perimeter must be minimized and p is the same as 2 times x is 4 plus 4. So that is now, okay, that is again 16, okay? Okay, so that is the smallest perimeter possible is 16, and when x and y are the same as 4, which means square. So for rectangular domain, once it's square, then perimeter is minimized. Okay. Okay, let's go to here second example. Now, 2048 feet cubed open top rectangular tank, rectangular tank with a square base x feet on a side and y feet depth is to be built with its top with the ground to catch round the better. Okay, so here and the volume is this one. Okay, now what dimension of the tank will minimize the weight? The minimized weight means that minimize the surface. So a volume is given. Now we have to minimize surface. The minimize the weight means just the surface area must be as small as possible. Okay. Okay. So here there are two things. One is volume. So let's try to visualize the tank. Here's open top rectangular tank like that, and one side in the bottom, square bottom, is x and deep is now y. So the volume is x squared y, which is the same as 2048. That is given. Now for surface area, we have to minimize it. Now what is surface area? Okay, each side, that one, will be xy. There are 4 sides, xy. And now we have a bottom, that is x squared. The bottom is okay, with square base x on a side. Now open top, so there is no side here. So this is surface area. We want minimize this so that must be minimized. Okay. So here one is volume, the other one is the surface to be minimized. By using the equation, we may express this surface area as a function of one variable. Okay. From this one, now from this equation, let's try to solve it for y. Then y column here, that is 48 divided by x squared. Okay, Now, or you can get here from this one, because we need the xy, so that xy equal 2048 over x, the same anyway. So we have here now for the surface area, and xy can be replaced by 2048 divided by x. So there are 4 times 2048 divided by x plus x squared. Okay, now it is a function of one variable, so we can use derivative technique. Of course, here s prime, the prime is the derivative with respect to x. Okay, that one is the same as now 4 times 2048 and divided by x squared along with the negation. 1 over x, the derivative of 1 over x is minus 1 over x squared. Now that is 2x. If we set it 0, then we can find the solution in this way. Okay, 2048 is, okay, that is 2 to the 11. Okay, so it's 2 to the 2, so that can be written in this way, minus 2 to the 13 divided by x squared plus 2x equals 0. That means that here, now divided by 2, so that 12. So here we can get now an x squared will be multiplied. So x cubed equal same as 2 to the 12. Okay. So we can see that x equal 2 to the 4, which is same as 16. When x is 16, and from that equation, you can find y equal 8. Okay, so we found the dimensions. Here, in earlier example, we didn't check if it is really here now minimum, but here you can check it quite easily with now x of s prime. Right now, okay, for that quantity, we found that when x is 16, the quantity is 0. Now here, but once x is smaller than 16, then that is now, okay, and smaller than 16, then this quantity relatively, and this quantity will be larger, okay, so that here, okay, that will be s prime will be negative when x is less than 16. Okay. And then now s prime is larger than 0 when x is larger than 16. So from here you can check it quite easily. That means that and left hand side the s is going down, and right side of 16 s is going up, which means that at x equals 16 it has minimum value. Okay, in this way you can check it. In your level, once you can find one critical point, then that point is in the value at the critical point is what you need. Okay. Okay, let's see next example. You have been asked to design a 1 liter can shaped like a right circular cylinder, as in this figure, and what dimensions will use the least material. Okay, again, we try to minimize the surface area. Okay, for this container, can, and now surface areas, now in the beginning, bottom and top is pi r squared, and two of them, so it's a 2 pi r squared. And the length of the perimeter is 2 pi r, and h is height, so that the side will be 2 pi r h. And also here now the volume is 1 liter, so that basically along with centimeter scale, and pi and r squared, the area times the height is so that pi r squared h is 1,000. Okay, that is a centimeter cubed. So that we'll here the unit is a centimeter unit. Okay. Now in this way we can formulate the quantities, area, and here the volume. So what we have to do is here minimize the area. Okay. Here. Okay, let's rewrite here. The A equal 2 pi r squared and plus 2 pi r h. And we have here now pi r squared h is 1,000. Okay, from this one, and we have to express this area as a function of one variable. But right now, here, R and H are involved, so that probably we have to replace H by using as a function of R, okay, so that from this equation we can express it. Anyway, here what we need is pi RH. So here from this one, pi, okay, RH is the same as now 1,000 over R. Right? Okay, so from this one, A can be written 2 pi R squared, and then plus twice of pi RH, that is same as 1,000 over R. Now it is a function of one variable, so using the derivative we can find the critical point. Okay, here A prime, the derivative with respect to R, there's now 4 pi R, and 1 over R, the derivative will be minus 1 over R squared, so then minus, and the coefficient is 2,000, that is R squared. If we set it 0, then now here from this one, and now we move this into right side, and then multiply R squared and divide by 4 pi, so it's R cubed equal 2,000 over 4 pi, the same as 500 over pi. Right? So here we have R equal 1/3 power of that quantity. So let's say now 500 over pi and 1 over 3. And by using this one, and here R, by using that equation, you can decide here H. But if you do practically, then H will be twice of this R. Okay? So that's how we can find the dimension. Okay. The requirement is given is the volume is 1,000 cubic centimeters, and we want to minimize the material, which means minimize the surface area. And when we try to do that, here you have to choose r radius in this way, and height must be twice of that radius. That means that eventually the height is the same as the diameter. Okay? Okay, here a rectangular plot of farmland will be bounded on one side by a river and on the other side, 3 sides by a single strand electric fence with 800 meters of wire at your disposal. What is the largest area you can enclose, and what are its dimensions? Okay, this problem is also the area and perimeter problem. Okay, and we have to maximize area, the largest area. So once you we visualize the rectangular farmland, okay, in this way. So we are trying to make that way, and one side is there's no fence, and this is a river. So we want to make such fence, and that if we say that is x and it's y, then area will be xy. But here, and perimeter, the required length is same as, now here we have 2x and only 1y. The other side is river. Right? And here now, for that problem, we want to maximize area. That's what we have to maximize. Now, and that's given. Here that is 800. So from this one, now y can be written as 800 minus 2x. Okay, then, and area can be written x times y. Y is now 800 minus 2x. Let's rewrite this one in this way. 800x minus 2x squared. So now this is a function of one variable, x. Now we are using derivative. That's 800 minus 4x. If it is 0, then x must be here 200. So by using this equation, or by using that equation, x is 200, 400 is subtracted, so that y must be 400. Okay. Now, that is the dimension, but what you have to find is the largest area. What is the area? The area is same as 200 x times y and 400, right? So then 80,000 square meters. Okay. Okay, that's the answer. So that the problem is asking the largest area, that is the largest area, and then the dimensions, 200 and 400. Okay? Okay, now 216 square meter rectangular P patch is to be enclosed by a fence and divided into 2 equal parts by another fence parallel to one of the sides. And what dimensions for the outer rectangle will require the smallest total length of fence, and how much fence will be needed? Okay. Now, there's again here area, rectangular region, area of rectangular region is given, which is 216. Now, we want to minimize the fence length, so that for given problem, let's try to visualize the condition problem is explaining. Right now, this is a rectangular region. And then now we want to divide the region into two equal parts by another fence parallel to one of the sides, so that possibly like that. If we introduce variables for this side x, and this whole thing is y, then here the area must be xy, which is given 216, right? And the fence length, okay, that is now perimeter, not really perimeter. Let's try to use notation L, okay? The fence length will be, here now, for x, we have 3, and y, we have 2y, right? Now, what we have to optimize is the fence length. So we have to find the smallest total length of fence. So that is what we have to optimize. But this is now function of two variables. So we may try to express it as a function of one variable by using the given equation here. Area is 216. Right? So that from this one, y equal 216 over x. So that one is the same as now 3x plus 2 times 216 over x. Now it is a function of x, so that we can use here derivative technique. That is a 3. Now minus 216 times 2 is 4, 32, and divided by x squared. That equal 0. And from this one, you can get x quite easily. That is x squared equal same as 432 divided by here 3. That is 1, 4. Okay, what is that? 144. Right. So that from this one, x can be plus minus 12, but it must be positive, so that x is 12. When x is 12, from this one, this equation, you can find y. And now here we want to find you have to find is that dimension. So from x is 12, okay, let's try to decide the dimension. Y equal, 216 divided by 12. What is that? That is 13. No, it's 18, right? Okay. Divided by 12 is 18. Okay, 18. Yeah, looks like 18. Okay, so we found that it's 12 and 18. Now, okay, and there's dimension and how much fence will be needed. So another quantity we have to find is the amount of the fence. Okay, now that is exactly this quantity, so that here final answer must be 2x plus 3y, and that is here by using 12 and 18 you can finalize. That is now 24 plus that is 54, so that is 78. Okay, now we'll solve the final problem. Find a positive number for which the sum of it and its reciprocal is the smallest. Okay, this is problem of finding a positive number. Let's say that is x. Okay, now sum of it and its reciprocal, so that is x and 1 over x is as small as possible. Okay, so that is now f of x. We want to minimize x, and so we want to find x, which makes the function as small as possible. Okay, so the f prime equals same as 1 minus 1 over x squared. If it is 0, then we can say that x squared is 1, but we have to find the positive number, so x must be 1. So that the positive number we want to find is 1. Okay? Okay, this is the end of the section. Thank you.